Hello everyone, and I welcome you all to Study Room. I hope you all are doing great. So today we will be studying chapter 11 of class 9, that is work and energy. So let's get started. Energy required by living beings. All living beings need food. Living beings have to perform several basic activities to survive. Such activities are called life processes. So we need energy to perform the life processes. Okay, so let's see this together. How can you differentiate between these two videos in terms of energy? Simply, this person looks so tired, right? So he has lesser energy and she is full of energy, right? Very energetic, more energy, right? So let's look at some brainstorming questions. Why do some engines require fuel like petrol and diesel? Have you ever wondered why does this happen? Why do these engines require fuel like petrol and diesel? For energy, right? So internal combustion heat engines use the chemical energy of fossil fuels for their operation. These energies first convert the chemical energy of the fuels into heat energy, which is later on converted into mechanical energy. Okay. So why do living beings and machines need energy? For the survival, right? To perform life processes. In order to survive, all living beings have to perform many basic activities called life processes. And such activities need energy, right? The energy required for these processes is derived from the food they take. Similarly, energy is required by machines to perform various types of functions. So, most of you think that, like you say now that I have done so much work today, like you do homework and you say, oh, I have done so much work today. And for example, you are pushing, this rabbit is like pushing the rock, but there is no movement in the rock. But he's saying that, I have done so much work today. So I want to tell you all that in physics, for us, you doing homework at one place and this person pushing the block and there is no movement in the block, we'll say that your work done is simply zero. For us, work is done if there is either there is some movement, right? We need movement. If force is applied, we need some displacement. Then only we'll say that some work is done. Okay. So if you are sitting at one place and you are watching me, so you are not doing any work. Okay. For physics, your work done is completely zero because you have no displacement. Okay. So working hard to push a huge rock, and if the rock has no movement, so you have no work. Okay. No work is done. The rock does not move despite all the effort and completely exhausted, right? So for us, work done means we need some movement, some displacement. Okay. What is this work done? No work in pushing a huge rock because there is no movement, right? So, scientific conception of work. Push a pebble lying on the surface, the pebble moves through a distance. Force is exerted on the pebble and the pebble got displaced. In this situation, work is done. So see, if the pebble got displaced, there is displacement. If you are applying force, okay, if you are applying force, and there is some displacement, okay, then we'll say that work is done. So in this case, there is work, right? But in a case, for instance, if no pebble would have got displaced, then your work done would have been zero. So in this case, if your pebbles got displaced, so you have done some work, right? You are sitting and doing homework, no work. You're doing no work in that case. So what are the conditions for work done? So there are two conditions which need to be satisfied for work to be done. Firstly, a force should act on the object. Secondly, the object must be displaced. There should be some movement. There should be some change in position. Only in that case you will say that some work is done. So how do we define work done? Yes, we define work done. Okay. So how do we define work done? Work done is defined as force into displacement. Since we know that our work done depends on these two things, our force and our displacement. So we say that work done is equals to force multiplied by displacement. Okay, so if any one of the condition does not exist, work is not done. Okay, so both the conditions need to be satisfied. A bullock is pulling a cart. Okay, so cart is pulled. The cart moves. There is the force on the cart and the cart has moved. Of course, see, force is applied by this bullock and the force is not wasted. There is displacement attached to it, right? The cart is moving. So since there is force and displacement, both the factors, we say that work is done. Okay. Work done by a constant force. Work is defined to be equal to the product of force and displacement. Okay, so what is the work done by the constant force? Work done is equals to force into displacement. F into, and how do we denote displacement? By S. So W and work done by W. Work done W is equals to F into S. Okay. Moving further. Work done by a constant force, right? Work has only magnitude and no direction. As we know, work done is equals to force into displacement, right? For work done, we don't have any direction. Because we are not supposed to know in which direction the work is happening, right? Work done is a scalar quantity. Okay, work done is a scalar quantity. It has only magnitude. Work done by a force acting on an object is equal to the magnitude of the force multiplied by the displacement moved in the direction of the force. W is equals to F dot S. Okay. So units of work done. Let's quickly derive it. We know that work done is equals to F into S. What is the SI unit of force? Newton, right? What is the SI unit of displacement? Displacement is calculated in meters. So what is the SI unit of work done? It comes out to be Newton meter. Okay. In multiplication, Newton into meter, Newton meter. Okay. So this Newton meter is also known as joule. Okay. Just like your force, we used to denote it by N, Newton. Just like that, a work done is denoted by Newton meter as well as by joule. So joule is equal to Newton meter. Okay. Thus, 1 joule is the amount of work done on the object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. So when do we say that 1 joule of work is done? If we know that work done is equal to force into displacement. If our force is also 1 Newton and our displacement is also 1 meters, then we say that work done is 1 joule. Okay. So 1 joule of work. This is how we define it. Okay. So let's do example 1. A force of 5 Newton is acting on an object. The object is displaced through the 2 meter in the direction of the force. If the force acts on the object all through the displacement, work done is, simply we know work done is equals to force into displacement. Okay. So what is force? 5 Newton into what is your displacement? 2 meters. Is equals to 10 Newton meter or 10 joule. Okay. Let's do one more example. A force of 7 Newton acts on an object. The displacement is say 8 meter in the direction of the force. The force acts on the object through the displacement. What is the work done in this case? Simply again, work done is equals to force into displacement, we know. Displacement and force, both are in same direction, both will take positive, right? If, for example, there is some case when your force is in this direction, displacement is in this direction, so we will take the displacement negative in that case. But in this particular case, we have force also acting in this direction and displacement also taking place in right direction. So we will simply multiply force and displacement. 7 into 8, that is your 56 joules or 56 Newton meter also we can say, right? Because SI unit is Newton meter as well as joules. But joule is the most commonly used unit, right? Sign convention of work done. The work done can either be positive or negative or 0, right? So either work done is positive, work done greater than 0, or work done is equals to 0, and third case, work done less than 0. Let's discuss all the three cases. For example, if a person applied force in this direction and displacement also occurs in the same direction, in this case your force and displacement, the direction of both is your positive, okay? So we say work done is greater than 0. Okay, so when is work done is equal to 0? If there is no displacement, then your work done is equals to 0. So no work done, in short, right? Third case, when your work done is less than 0. When did this happen? When do this happen? When your force is applied in one direction and your displacement takes place in another direction, okay? So negative direction. Then we say our work done is negative, okay? So that is a kind of retarding force, right? So let's quickly read this. If force and displacement are in the same direction, then the work done by the force is taken as positive, work done greater than 0 in this case. Secondly, if a retarding force F is applied in the opposite direction, then the work done by the force F is taken as negative, work less than 0. So work done by the force is either positive or negative, right? Also, not only this case, we can also see if force is acting in left direction and displacement acting in right direction, then also your work done is negative, right? Opposite directions, okay? So F into, either it will be F into minus S or minus F into S. So in the axis, we take this direction as negative and this direction as positive, right? So for example, in this case, if your F is acting, force is acting on the right direction, so force is positive plus F, and your displacement is taking place in the left direction, negative S, right? F into minus S in this case. And if your force is acting in the left direction, so force is negative and your displacement takes place in the right direction, plus S, minus F into S. So we see work done will be negative in these cases, okay? So we have three cases for work done. Either work done is greater than 0 when both are in the same direction, or the work done is equal to 0, that is no work done, or the work done is less than 0, okay? So let's do this question number 1. A potter lifts a luggage of 15 kg from the ground and puts it on his head 1.5 meter above the ground. So this is a potter, okay? He took the luggage and put it on his head, okay? Calculate the work done by him on the luggage, okay? So let's calculate this, okay? So let's quickly do this, okay? So if this potter, he's standing and he has this luggage, so what will be the force? Force is equals to mass into acceleration. So he is standing, so what is the force acting on him? M into G, right? And take G as 10 meter per second, okay? So what is your force? Force is equals to 15 kg into 10 meter per second, that is your 150 newtons, okay? This much force is applied, okay? Then what is your, and displacement? He's taking this from here to here. He's taking his luggage, okay? So how much displacement? 1.5 meters. S is equals to 1.5 meters. What will be your work done? Work done is simply F into S. So your F is 150 newtons and your displacement is 1.5 meters. So how much is your work done? 225 joules, Okay. Right, or we can also say 225 Newton meter. Okay. So when do we say that work is done? We studied two conditions. Work is done. We know that work done is equals to force into displacement, right? So when do we say that work is done? First condition, force should be applied. Second condition, there should be change in position. Change in position should take place. That is your displacement. Okay. Write an expression for the work done when a force is acting on an object in the direction of its displacement. Okay. So your work done is equals to force into displacement. If force is also acting in this direction, let's say 10 Newton, and displacement also occurs in this direction, let's say 5 meters, for instance. If both are in same direction, your work done will be positive. Okay. So let's write this. So simply, what is the expression of work done? Force into displacement. Next slide. Define 1 joule of work. We have already done this. So let's do this question. A pair of bullocks exerts a force of 140 newtons on a plow. So your force is 140 newtons. The field being plowed is 15 meters long. Okay. The field which is being plowed is 15 meters long. How much work is done in plowing the length of the field? So if we are plowing the length of the field, then we have to plow this 15 meter long field, right? So what will be our displacement? It will be 15 meters. And we have to calculate the work done. Isn't that simple? We know work done is equals to force into displacement is equals to 140 into 15, and which is equal to 2700 joules, correct? 140 into 15 is equals to 2100 joules. Sorry, I just read 2100 joules, okay? So now we are going to start with the topic energy. Are you full of energy to study energy? I hope you are. So let's get started. Energy and its sources. Sun is the biggest natural source of energy. We all know our sun, right? So sun is the biggest natural source of energy. Okay, energy is obtained from the nuclei of atoms, the interior of the earth, and the tides. Illustration of energy possessed by an object. Work is done while winding the key of a toy car. Energy transferred to the spring inside is stored as potential energy. Basically, energy conversion. For example, in your homes, you see that, the light is lit. So your chemical energy, electrical energy is converted into light energy, right? So there are different forms of energy, and we can transfer from one form of energy to another, right? Like the energy transferred to the spring inside is stored as potential energy. Okay, what is potential energy? Basically, it is an energy at some height, okay? The potential energy possessed by the object is the energy present in it by the virtue of its position or configuration. Correct? So, definition of energy. An object having a capability to do work is said to possess energy. Capability to do work, okay? The object which does the work loses energy, and the object on which the work is done gains energy. For example, let me give you one example. For example, you are pushing a block, okay? You are pushing a block, you are applying force to it, and you are, using a lot of energy. So here you are losing energy, and the block gets moved, okay? So block is getting energy, right? For example, you can see of light. All of you might have like tube lights or bulbs in your homes, right? So there also, electrical energy gets converted into chemical energy, the light energy, right? So electrical energy is lost and you get the light energy. So one object loses energy and the other object gains energy, okay? An object that possesses energy can exert a force on another object. When this happens, energy is transferred from former to the latter. So units of energy. The energy possessed by an object is thus measured in terms of capacity of doing work. The unit of energy is same as that of work, that is joules. Okay, unit of energy is same as unit of work. What was work? Work was nothing but force into displacement, Newton meters or joules. Energy is also measured in joules, okay. 1 joule is the energy required to do 1 joule of work. A larger unit of energy called kilojoule is also used. Okay, so kilojoule, for example, when we talk about, electricity consumption in your house, we deal with kilojoules. Joules will be very small, right? So we deal with kilojoule, and 1 kilo is equals to 1000, right? So 1 kilojoule is equals to 1000 joules, okay? You should know this conversion. So let's study forms of energy. The various forms of energy are mechanical energy. Mechanical energy, like from the manual work you do, right? Heat energy, from the dissipated heat. Chemical energy, from chemicals. Electrical energy, from electricity. And light energy, from light sources, right? So the two forms of mechanical energy are potential energy and kinetic energy, okay? So let's explore this together. So the bullet pierces the target due to the kinetic energy. Since the velocity of the bullet is too high, so it pierces the target. And how does the wind move the blades of a windmill? Due to wind energy, right? The movement of turbine and conversion of energy into wind energy. So can you just see that energy plays a very important role in our lives, right? So let's do an activity to demonstrate kinetic energy. So what did we do? We took 3 blocks. In one block, we put some balls, so to roll it, okay? So to push it, okay? And then like some force is being applied. So you see force is applied and displacement occurs since this like the block which is attached by a thread, it goes downwards, right, as you move this block since it is attached to the thread. So what did we see? That there is change in position. So we have a mass of the object, we have the velocity with which it is going. So we say that kinetic energy is equals to half mv square. This is how we define kinetic energy. We'll learn further about this. So let's study about kinetic energy. So basically kinetic energy is energy due to the virtue of motion. Okay. So let's see. A moving object can do work. An object moving faster can do more work than an identical object moving relatively slow, right? A moving bullet, blowing wind, a rotating wheel, a speeding stone can do work. All of them possess kinetic energy, okay? Objects in motion possess energy termed as kinetic energy. See, you can see kinetic energy in this also. So kinetic energy, it is the energy possessed by an object due to its motion by the virtue of motion. Okay, so we possess kinetic energy by the virtue of motion. Kinetic energy of an object increases with its speed. A falling coconut, a speeding car, a rolling stone, a flying aircraft, a flowing water, blowing winds, running athlete, etc. possess kinetic energy. So definition of kinetic energy. Kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Okay. So equation of kinetic energy. Force acts in the direction of the displacement and work done is Fs. We know that if force is also positive and displacement is also positive, Okay, then also our work done is force into displacement. Both are in this direction. If force is negative and displacement is also negative, then also your work done is equals to minus F into minus S. That is also positive, right? So, right, if both force and displacement act in the same direction, our work done is positive, right? Work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let a be the acceleration produced. Acceleration is rate of change of velocity, right? Okay. So this is how we derive the equation of kinetic energy from, what was this? Yes, you're right. This is third equation of motion. So we'll derive the equation for kinetic energy from third equation of motion. So the relation between initial velocity and final velocity of an object moving with a uniform acceleration and displacement s is v square minus u square is equal to 2s. Yes, we derived this in our chapter motion, right? So your s becomes v square minus u square upon 2a. Okay. Now your force is equals to mass into acceleration, right? What did your s displacement became this, right? Now your force is equals to mass into acceleration. So work done is also equal to work done by force is equals to work done by force is also equal to mass into acceleration, right? Is equals to mass into acceleration. And what is your acceleration? M into v square minus u square, right? Half m into v square minus u square, right? How did we get this? We know that force is equals to mass into acceleration. From here we get acceleration is equals to force upon mass, right? We put acceleration is equals to force upon mass in this equation, right? We'll just do this, okay? So your s becomes v square minus u square upon 2 into f by m. So your m will go upwards, right? It will become half m v square minus u square, right? So your work done by force is equals to half m v square minus work, and this is your work done by force, right? So this will go there. Let's do it more clearly, okay? I hope I explained to a great extent, right? We put s is equals to v square minus u square upon 2 into what is your acceleration? Force upon mass, correct? So what will we get? We'll take f into s, f to the, we'll send f to the left hand side. So it will go into multiplication because here it is in division. F into s is equals to v square minus u square upon 2 by m, right? So m will go in the numerator, right? So f into s is equals to half m into v square minus u square, and this is nothing but your kinetic energy, right? This is a type of work done, right? So work done is equals to half into m v square minus u square. This is how we derived this, okay? From mass, and we know force is equals to mass into acceleration, okay? So work done is equals to force into displacement, and s is equals to v square minus u square by 2a, and this is how we derive, okay? Force into displacement, work done is equals to half into m into v square minus u square. If the object is starting from its stationary position, so if u is equals to 0 in this formula, then this will be half m into v square minus 0 square, which will be nothing but half mv square. Okay, so this will be your kinetic energy. Equation of kinetic energy. Work done is equal to the change in the kinetic energy of an object. If your initial velocity is 0, work done will be half mv square, because if your u is 0, so in your formula, u will become 0, right? Thus, the kinetic energy possessed by an object of mass m and moving with a uniform velocity v is energy is equals to half mv square, kinetic energy. So let's do one example quickly. An object of mass 15 kg is moving with uniform velocity of 4 meter per second. So mass of your object is 15 kg. It is moving with a uniform velocity of 4 meter per second. Your velocity is 4 meter per second. So what is your kinetic energy? Kinetic energy is nothing but half mass into velocity square, right? Half into 15 into 4 square, right? Half into 15 into 16. What does it come out to be? 120 joules. Okay, so this is your kinetic energy. Let's do one more question. What is the work to be done to increase the velocity of a car from 30 km per hour to 60 km per hour if the mass of the car is 1500 kgs? Your mass is 1500 kgs. What is your initial velocity? Initial velocity is 30 km per hour. We will quickly convert it into meter per second. (25 by 3 meter per second). Okay. And what is your final velocity? Your final velocity is 60 km per hour. 60 into 5 by 18, right? Again, we'll convert it into meter per second. Is equals to 50 by 3 meter per second. And what is your work done? Work done is nothing but half mv square minus u square. Okay. So it is your half into 1500 into what is your v square? 50 by 3 square. It's 5 5 is 2500 by 9 minus 625 by 9. Right? V square minus u square. Let's quickly solve this here. So work done is equals to half into 1500 into what is 2500 minus 625. Let's quickly calculate. Into 1875 by 9. Okay. So we'll just calculate it. So your work done is, so we just quickly multiply these, okay, and so we get that the work done is 156187 joules, okay. This is almost 156.18 kilojoules, okay. See how much, like a large amount of work is done. So what is the kinetic energy of an object? We just discussed it in detail. Write an expression for the kinetic energy of an object. We know kinetic energy of an object is given by half m v square minus u square. We just derived it in the previous slides. One more question. The kinetic energy of an object of a mass m moving with the velocity of 5 meter per second is 25 joules. So work done is given to be 25 joules of mass m moving with the velocity of 5 meter per second. What will be its kinetic energy when its velocity is doubled? So if your velocity is doubled, so your new velocity is how much? Your new velocity is, velocity new is your doubled. Double of 5 is 10, right? 10 meter per second. So what will be its kinetic energy when its velocity is increased, when its velocity is doubled? So firstly, your kinetic energy initially is work done, like kinetic energy is how much? 25 is equals to half m 5 square, half mv square, right? So what is your mass? Let's calculate the mass. Mass is 50 by 25 is equals to 2 kgs. Now you know that your mass is of 2 kgs, okay? So now your new velocity is 10 meter per second, mass is 2 kgs. What is your kinetic energy? Kinetic energy will be half mv square. What is your v square? 10 square, that is 100. Kinetic energy is 100 joules. And if your velocity is increased 3 times, if your velocity becomes 3 times, that is your 3 times 5 meter per second, that is a 15 meter per second. So in third case, what will be your kinetic energy? Kinetic energy again, it's half mv square is equals to half into what is your m? 2 kgs into v square, 15 square, that is 225 joule in the third case, okay. So thank you so much. We'll meet in the next video and we'll discuss in detail about the potential energy. Till then, do revise, do ask doubts and solve questions. Bye bye, and we'll meet again in study room.